I'm Scott Maxwell. I'm a Mars rover driver, and this is your Curiosity update. Through careful targeting, we've been able to shrink the landing ellipse for Curiosity, and we've been able to move it closer to where we want to actually land. In case we land in dunes that are like this on Mars, near the landing site, we want to be sure that the real rover is able to navigate around successfully in those dunes and get from the point where we landed to the point where we really want to be. So we've come out here today with the Curiosity Scarecrow rover, which is the same weight on Earth as the real rover is on Mars, to practice driving it around in the nearest thing to those dunes on Mars that we're going to find here on Earth. This is similar material and similar slopes to the dunes that we're going to find in Mars. So being able to test this rover in these dunes gives us a good idea about what the performance of the real rover is going to be in the dunes that we might land in on Mars.
Still making progress.
The performance on this rover is actually fairly similar to Spirit and Opportunity. A little bit better. We can climb in soft sand up to about 15 degrees or so, which is a little better than Spirit and Opportunity will do. We are in fact right now maneuvering it from an area of about 15 degrees of tilt to an area of about 25 degrees of tilt to try to explore where that break is in its performance. Our top speed is very slow, but our acceleration of that top speed is pretty much instantaneous. So we go from a dead stop to right about as fast as we're going to go pretty quickly. And it's really fun to, like, every once in a while, kind of leave the office environment behind and come out to an environment like this and see what the real rovers are going to be doing on Mars. It kind of connects you to it and reminds you that, that the computer models that we play in are a far cry from reality. This is that reality. I'm Scott Maxwell, and this has been your Curiosity Update.
Hi, I'm Chris White, System Engineer leading the Integrated Sample Chain Test Program, and I'm here with your Curiosity Update. Today I'm standing in the MSL Vehicle System Test Bed with a test model of Curiosity rover, and we're about to do a scooping and sample drop-off test. So in today's test, we'll bring the scoop on the end of the arm down into this tray of specially prepared sample. We'll be taking images and identifying the target where we want to actually scoop. Then we'll move the arm over, open up the scoop. We'll scoop a sample of material. We'll close the scoop. We'll bring the arm back up to the front of the rover, and we'll drop a very small portion onto the observation tray. Then we'll spin the turret around and take additional images of the portion on the sample tray. Once we've acquired those images, we'll bring the turret around again and drop off a portion into the inlet covers on the top of the rover. The sample we need is not very big at all. In fact, it's about the size of this aspirin I'm holding. Once that portion is dropped in, it will go into the science instrument SAM. And when we're done with that, we'll bring the arm back out and we'll clean everything out. We have automatic cleaning functions that we do to clean everything out, ready for the next sample. This has been your Curiosity Update.
Hi, I'm Ashwin Vasavada, the Deputy Project Scientist for the Mars Science Laboratory mission and its Curiosity rover. So a lot of people wonder why Curiosity doesn't have solar panels like the Mars Exploration rover, Spirit and Opportunity. The Mars Exploration rovers often found themselves short on power as dust settled on their solar panels. This was especially a problem in the short days of winter. We need a good, strong, and reliable source of power to keep Curiosity going for over 2 years on Mars. Curiosity is 2 times bigger, 5 times heavier, and has 15 times the weight of scientific equipment relative to Spirit and Opportunity. Like those rovers, Curiosity surveys the landscape and examines rocks up close. Curiosity's scientific mission involves driving around its landing site, perhaps up to 15 or 20 miles, collecting samples of rocks and soils with a big jackhammer drill located on the end of a 6-foot robotic arm. Those samples are delivered to the rover and analyzed with some very sophisticated and power-hungry analytical laboratory instruments. And that's where the MMRTG comes in. The multi-mission radioisotope thermoelectric generator is a power source that we've used for years to power spacecraft that have gone to the outer planets, and even the Apollo missions used it on the moon. Behind me you can see a full-scale model of Curiosity, including the generator in the back. On this half-scale model of the generator, you can see what's inside. The generator contains a specially produced form of plutonium dioxide. The natural decay of this radioisotope gives off heat, which these thermocouples can turn into electricity. The generator provides both electrical power and heat to the rover. About 100 watts of electrical power is used to continuously charge the rover's battery. Also, heat can be pumped off of the generator using pipes to keep the rover's insides warm, including the scientific instruments. With Curiosity's generator, there's a guaranteed way of charging the battery year-round in all sorts of conditions. Curiosity's generator was developed by the Department of Energy and will be installed on the rover just a few days before launch. But to make sure everything works together properly, the engineers installed the actual generator on the rover for the first time. The blue light that you see was just additional lighting to help them make sure they could see what they were doing. The Curiosity rover and the spacecraft that'll take it to Mars are currently in Florida, undergoing its final preparations for launch. Everything's going well, and all of us on the science team can't wait for its launch later this year and its arrival to Mars next summer. I'm Ashwin Vasavada, and this has been your Building Curiosity update.
There's the dust down at the surface.
Da ist der Staub. Wir wirbeln viel Staub auf Houston.
Picking up a lot of dust, Houston. So there they are moving away.
Für den Laien ist nicht viel zu sehen auf den ersten Videos, die der NASA-Roboter Curiosity zur Erde sendet. Der etwa kleinwagengroße Rover war am Montag auf dem roten Planeten niedergegangen. Die Bilder zeigen den äußerst komplexen Landevorgang auf der Oberfläche des Mars. Auch ein erster Test der Geräte, die Curiosity an Bord hat, ergab keine größeren Probleme, erklärt die US-Raumfahrtbehörde NASA. Neben der unmittelbaren Umgebung mit dem Schatten des Roboters zeigen die ersten Bilder vom Mars einen Panoramablick auf den rund 5000 Meter hohen Mount Sharp. Im Laufe der mindestens 2-jährigen Mission soll Curiosity den Berg erklimmen, um dort Bodenproben zu nehmen. Sie sollen Aufschluss geben über die Geschichte des Planeten und mögliche Sedimente, die auf Wasser oder Leben hindeuten könnten. Den ersten eher unscharfen Bildern sollen in den nächsten Wochen hochauflösende Fotos von der Marsoberfläche folgen. Außerdem nimmt Curiosity Bodenproben und schickt deren Analyse zur Erde. Dabei soll der Roboter vor allem Sulfate und Tonminerale unter die Lupe nehmen, die auf Wasser hindeuten könnten. Und irgendwo in den Ablagerungen, so die Hoffnung, könnten sich vielleicht auch Spuren von mikrobiologischen Lebewesen oder Versteinerungen verbergen. Die Menschheit kann sich zudem auf jahrelange Eindrücke vom Mars einstellen. Curiosity ist mit einem kleinen Plutoniumreaktor ausgestattet, der theoretisch jahrzehntelang Energie liefert.